Estimate the activity coefficient of cyclohexane in benzene 1 cyclohexane 2 at 343 Kelvin for a mole fraction of cyclohexane of X2 equals 0.25. In order to find the activity coefficient for cyclohexane with the mole fraction of 0.25, you have to first find the value of A from the two suffix modules equation. Because the graph references excess Gibbs free energy over R, you have to divide both sides of the equation by R. Solving for A over R, you'll get excess Gibbs free energy over R times the mole fraction of X1 times X2. Using the graph given in the problem statement and choosing any value of X2, here we chose 0.5, you'll find that the value of GE over R is 31. Solving the equation that we put together for A over R, you'll also find that A over R is equal to 124. You'll need this number for further calculations, so keep it. In the problem statement, you were told that X1 is equal to 0.75 and X2 is equal to 0.25. Referencing table 7.2 again, you'll find that RT ln of the activity coefficient is equal to A times the mole fraction of 1 squared. So plugging in the initial conditions, 0.75 squared times A over RT raised to the power E will give you the activity coefficient. In the problem statement, they told you that the temperature was 343 Kelvin. Once you plug in all the values, you'll find that the activity coefficient is equal to 1.22.
Part A2. Estimate the activity coefficient for cyclohexane in benzene 1, cyclohexane 2 at 343 Kelvin for cyclohexane in infinite dilution.
So, looking at part B, we know that the activity coefficient is equal to E raised to the A times the mole fraction of 1 squared all over R times T. Because we're doing an infinite dilution problem, we know that the mole fraction must be equal to 1. So now, we're going to plug in all our values to get the infinite dilution of the activity coefficient. So, looking at our previous answers, we know that A over R is equal to 124 multiplied by x1 squared, which we know is equal to 1 since it's infinite dilution, and we're going to divide by 343 Kelvin. All of this is going to be equal to 1.44. And that's your answer.
Part B. Estimate the Henry's law constant for cyclohexane in benzene. To solve for Henry's law constant for cyclohexane and benzene, the equation we'll be using is the constant set equal to the activity coefficient at infinite dilution times the fugacity of cyclohexane. To make the calculation simpler, we'll be assuming that the pressure of the system is low, and therefore we can say that the fugacity is equal to the saturation pressure of cyclohexane, and then we can plug this back into the original equation. To solve for PSAT, we'll be using Antoine's equation. This can be written as PSAT is equal to E to the A minus B over T plus C. A, B, and C are Antoine's coefficients and can be found in the back of the book in table A.1.1. In this case, A is equal to 9.1325, B is equal to 2766.63, and C is equal to negative 50.50. If we take these values and plug them into the equation, along with T being set to 343 Kelvin, as it is said in the problem statement, you'll find that PSAT is equal to 0.7218 bar. From part A, we already found the activity coefficient at infinite dilution for cyclohexane and benzene to be 1.44, so we will use that value in the equation. By taking those values and multiplying them together, so 1.44 times 0.7218 bar, you'll find that the Henry's law constant for cyclohexane and benzene is 1.039 bar, and that is the final answer. Part C. Are the like interactions stronger or weaker than the unlike interactions? Explain.
So for part C, the question is asking you whether the like or unlike interactions are stronger. And we know that the like interactions are stronger because the value for A is greater than 0. And also we know that the like interactions are stronger because the Gibbs free energy is greater than 1.